I wanted to mention something to you guys, if this is helpful. Might not be. You might already have it figured out, but okay. So if you are, it'll take a second. The graphs that we were doing yesterday,
I'm sorry, I'm a little hungry.
You take the straw out of the wrapper.
I'm not gonna use a straw.
all right. Sorry, you guys are missing out on Anderson trying to inhale a milk box or something. All right, so yesterday, or over the past 3 days, we've been talking about polar graphs, and yesterday we talked about kind of the stranger versions of those. Up until last year, I didn't even mention these. They're not on a regular pre-cal radar, but they kept showing up on math tournaments. And they're not overly difficult to get even if you forget some of these rules. What you could do, remember, and you can do this, is just plug in degree values. So like if I was trying to figure out what this was, let's just say it was a multiple choice question and it said, what is the equation of this graph? All right, and they gave you a whole bunch of options and they all look very similar. I mean, one thing that you could do is just start plugging in values in there. Like I can look at this and I can say, well, that's 15, that's 30, that's dead in the middle, 22.5. If I plug 22.5 in there and there and there and there, only one of them is going to give me a value of 8. Like 4 times 22.5 is 90. Sine of 90 is 1. 1 times 6 is 6 plus 2 is 8. That's 8. Here at 22.5, when I try that, I don't get 8. Okay? So a lot of times you can actually figure these out without these rules. But to kind of help you, we talked about little patterns that I have noticed, and I'm trying to make it better every year. Yes, last year the notes I came up with were kind of suspect at best, so I redid them for you yesterday. And you guys at home, there's a better version of that if you want to print that out. But one thing I also noticed to kind of help you is, you remember with rose curves, which these are a little like the rose curve thing because of all the petals, but there's a kind of a discrepancy. It's like, why do these have 8 petals when they're even, which is, and I changed this, by the way. I was talking with my 7th period, and I think on your notes it says sine, sine, and then cosine, cosine. And I changed it up a little bit just so that you don't fall into the assumption that sine, sine has the small petals there in between, and cosines have the petal on the inside. It's not that. It is 4 even numbers with theta have the petals not in the same location, and odd numbers have the petals in the same location. But I thought of something that might help you link this to what you already know about rose curves. Do you remember how in rose curves, if it was even, you had twice as many petals, right? Right? And that's still true. I do have twice as many petals, and they're all in different locations like it would be on a rose curve. So I can still kind of think the same way, but I can find the first big petal by thinking like we did yesterday, where would this be maximized? Now, remember on rose curves with odd numbers there, how many petals did we have? Hello? That many? Well, actually we didn't. Do you remember what happened when I graphed it? They were overlapped, right? So they were there were still 10, but because they were in the same location and the same size, you only saw 5 of them. Well, this time there are still 10, but because they're in the same location but different sizes, you see the smaller ones. But on a rose curve, when it was an odd number, because they were all the same length, you didn't see but those 5. So if that kind of helps you remember when they're in between the big petals or when they're inside the big petals, That's how my brain's thinking. But again, if you already have that memorized and have a way to remember that, great. Because all of these will be mixed up on your test. Are you with me on that? Okay, does anybody have any more questions on anything to do with polar? And I want to mention a couple things that I don't care about, but they're still on my keys. Like, there is something called a polar axis. And a polar axis, technically, is from the pole towards 0 degrees. And there's also a line called theta equal pi over 2. And the line theta equals pi over 2 means anything that points to pi over 2, that line, it's kind of like the y-axis. And people use the polar axis loosely, and they kind of refer to it as the whole, what would be like the x-axis, and the theta over 2, because you could have a positive r value at theta over 2, right? That's theta over 2. I'm sorry, not theta over 2, pi over 2. You could have a positive value at pi over 2 for r, but also a negative value. Are you tracking with me? So that vertical line represents that. I don't really get into that on my test a lot. I mean, there might be a mention, but if there is a mention, polar axis is kind of this thinking, and pi over 2, the line theta equals pi over 2 would be this axis. But again, that to me is not what ever gets tested at these math tournaments. Mostly is understanding what the graphs would look like. And then another thing I think I mentioned a lot of times, what are the coordinates of the maximum R values? So like on a curve like this, the maximum R values occur there and there and there and there. So I would be looking for the R's and the thetas. Like this would be 8, 22.5. This would be 8, 112.5. Are you tracking with me? But that's probably not something, I'm going to ask you to graph them, so you're going to have to know that. But I don't recall on prior tests over the past few years me asking you to label all those. As long as they're in a really good spot. Now, if you're in the wrong place, that's going to cost you. So you're going to have to find them. But I don't do a lot of the labeling like I did on some of those review sheets. Is there anything else, though, you had a question that you were like, man, I didn't know how to do this, or what the heck are you asking? Because we're about to move into projectile motion. Anyone? Okay. So I was looking at it. I didn't plan on spending 3 days going over those graphs, but it kind of took that because normally we don't do as much with this, what we've been talking about right here. So we're going to bump everything back a day. Okay. So if you did review number 2, great. But literally, when you look at your assignment sheet, what we're going to do Wednesday is really Tuesday's work. So we're going to get through classwork, projectile motion, and really there's not going to be any homework with that. And then what it says for 2-3, what it says for Wednesday on your sheet, that's what we're going to do Thursday. What it says for Friday on your Thursday on your sheet, we're going to do Friday. And what it says for Friday, which is your test, we're going to have on Monday. So we're just going to bump everything back a day. I don't know if you hate a Monday test. I used to not like that, but this way we won't just be cramming it in there. We can actually just do it. I think we'll be fine. We're not behind in this class, and we don't have to prepare for 4 math tournaments or 3 whatever math tournaments. All we got to do is that state tournament, which honestly we won't even have to prepare as much for that because it's so late in the year. We'll have covered everything again, like we normally don't do that by February. All right. Okay, so make sure you make a note of that our test is on Friday. Hopefully you guys at home have heard that as well. Friday. I'm sorry, your test is on Monday. Okay, so I want you to jump to the classwork, and which for projectile motion, which is after review number 3. Okay, so do you remember when we were solving systems, just the last chapter, or even the last 2 tests actually that we took, and we were solving a system like, I don't know, maybe something like this. And there might have been a third equation too, and you got to solving and you got all zeros, like everything canceled out. Do you remember that? Or maybe like on the last test, I just gave you 2 equations and said solve. And because these 2 equations represent planes, when they intersect in a what? In a line. And you had to show me all the answers that worked. And the way you did that is you wrote your answer in terms of z. You remember that? So you had, after you did all the work and put it in, used Gaussian elimination or whatever it is you did, you ended up with answers that looked like z was z, and then maybe you had something like 5 minus z and maybe 2z plus 1, and you had your answers represented like that. Well, that was a way that you wrote parametric equations. You just didn't really know it unless I casually mentioned it. What I'm really saying by something like this is x could be 2z plus 1. Your y value could be 5 minus z, and your z value could be z. Except I didn't use z. I picked some other variable, usually t, because a lot of times we're talking about what's happening over time. So a lot of times we'll just plug a t in there. And these will represent parametric equations, or how a certain graph, maybe it's a parabola, maybe it's a line, like in this case, whatever it is, that will show how this thing is moving through 3 dimensions. And that's how we would write a set of parametric equations when you start moving through 3 dimensions. Because I can't treat it like slope. Slope only does rise and run. That's y and x. What's happening with the z? Okay, so in a situation like this, that's how I would represent movement through space. And it doesn't have to be linear like this one. Okay, so right here, that's parametric. And parametric says basically, I need to know where I'm going to begin. Give me a starting place. Kind of like when you're graphing a line, I need at least to know one point, right? And then from that point, what would I need to know about the line? Hello? Come on, guys. It's interactive experience. So if I start with the point, if you're going to move along a line, what do I need to know? A slope, right? I got to know my behavior, what's happening after that. So in this case, this would be like me starting at the point 1, 5, and since there is nothing added to t, 1, 5, 0. So this is like me starting at 1, 5, 0, okay? And then it's saying, okay, at this point, for any increment of time or any increment of whatever, whether t is 0.1 or 1 or 2 or 5 or whatever, the movement will be 2 spaces in the x direction, -1 spaces or down 1 in the y direction, and then +1 in the z direction. And it tells me what to do from that point. That's what parametrics do. They give me a starting point, which is represented by constants, like 1, 5, 0. That's where I'm going to start in the space. So maybe my fist represents that. And then after that, I'm going to move this much. For every t, I'm going to move that much in the x, that much in the y, that much in the z. It's kind of like my slope. So in this one, I would say move from this point 2 to the right. That would mean down 1, and then that would mean out 1. And that would give me another point, and then I just connect them. And I keep moving in that proportion through space. Now, this is an example, again, of a linear example. It doesn't have to be linear. You start putting squares and other junk in there, and all of a sudden, I am now curving through space. But I got to have a starting spot right here, and I have to have how much I'm moving in every direction. Those are parametric equations. And I could give you a lesson on parametric equations that means absolutely nothing, talking about more of this, figuring out more points or whatever, and boring you even further. But I'm not. What I'm going to do is I'm going to teach parametrics through something that's actually real life, something which is projectile motion. Like when I throw something, if I throw something, it's not going to go through the roof and out the ceiling and out through outer space. It's going to have an arc because of gravity, right? But it's going to move through space. And I technically, it's going to move through space in 3 dimensions. We're going to make life a little bit easier and cut out that 3rd dimension. And we're going to talk about parametric equations moving through space in 2 dimensions. So I know, like if you play baseball and you throw a ball, if you throw a ball and you put some spin on the ball, it actually will go up and it will actually curve and actually move in 3 dimensions, right? We're not going to deal with that. We're just going to pretend that there's no curve balls when we're shooting Biff out of a cannon or throwing a baseball or whatever it is we're going to be doing with our projectiles, launching a cat over a wall, whatever it is, we're going to be looking at the 2 dimensions of parametric. So we're going to basically break up a parabola and talk about its movement parametrically, okay? So from here on out, I'm going to be talking about projectile motion, but we're going to be using parametric equations to discuss this. And the great part about that is a parabola, when you graph a parabola on your calculator, it's like, boom, parabola, right? Now, in real time, a real parabola, when I throw, like, for instance, if I were to take this and throw it up, I'm going to do it in slow-mo. This thing is launched, it's moving very quickly, right? And what happens is it starts nearing the top. Slows down, and then as it starts to fall, it speeds up, right? Because there's a time component in there. So the actual movement is reflected by time. So as you're marking off time, 1 second, 2 seconds, 3 seconds, you can actually see this on a poorer calculator than yours. But I have one of those, the 84. So I will show you how it moves up really quickly, and then it slows down near the top because gravity is causing it to stop, and then start to accelerate back towards the bottom. And you can see that reflected as opposed to just a parabola that's graphed that doesn't have anything to do with time. So in our examples of projectile motion, you'll see a lot of this, but we need to talk about why our parametric equations are what they are. And clearly, this linear set right here is not going to do the trick, because we know that projectiles on this planet do what? Because of gravity, what do they look like? Do what?
They go down.
But what is that?
Arc.
It's a parabola. So these are quadratic. So we're going to talk about why they're quadratic. Now I'm going to get a little bit into the physics, a little bit into the calculus, which you don't understand. So for you guys taking Physics 1, you're taking a non-calculus based physics. You might see some of this and you're like, oh yeah, that's why. But you're not going to understand why it's -1/2 acceleration or why it's whatever, because you don't understand the calculus yet. But if you take Physics C next year, then you'll actually take a derivative and take an integral, and you'll see, oh, that explains to me why the math is what it is. But I can just kind of give you a hint about that right now. So anyway, I know I've just been chattering a lot, but that's kind of what we're doing for these last 3 days, Wednesday, Thursday, Friday, before, I think Friday we're just going to be reviewing all this stuff, but really for today and tomorrow, we're going to be looking at this projectile motion. So the first thing I want to talk about is how things move. So what we're doing with the projectile motion is we're taking this parabola, which is moving through along an X and along a Y, right? And we're going to separate those components, kind of like we did with vectors. Okay, remember with vectors, I had a horizontal component and I had a vertical component, right? Sometimes we would say X is 2, Y is 3, and we write 2, 3, but it represented a vector moving through space. So I'm going to kind of do that. So the first thing I'm going to talk about is this. If I shot something out of a cannon or whatever it is like this, it's going to have an X and it's going to have a Y component. Are you with me? So or you could think about that right here. I need to think about both of those. So if this was my velocity, and I use VO to stand for my velocity at time 0. Sometimes physics uses VI to stand for initial velocity, but VO is just our initial velocity. So if I shoot it, there are 2 components of velocity. There is an X component and a Y component. How am I going to find, if I know this angle, say the angle was 55 degrees, how can I find that and that component of the velocity?
Cosine 55 and then B0 sine.
Are y'all seeing? I'm just using trig, right? So I know that X right here, or the cosine of 55 is X over that, right? Adjacent over hypotenuse, and I'm going to multiply that VO over there, and there's my X coordinate. So what I'm going to do is say X is initially moving at this particular rate. Okay? That is my rate. Y'all seeing that? So if I want to know where X is located, and that's my initial rate or speed in the X component, I just need to figure out how far along I've had for each unit of time. Like if I'm going 5 miles per hour, at time 0, I'm nowhere, because 0 times 5 miles an hour would be 0. At time 1, I'm 5 away. At time 2, I'm 10 away. Are you kind of tracking with me? So I tack a T on there to show how far I've moved in that direction. Okay? Now, when I'm graphing these, if I'm dealing with an X and a Y coordinate, I'm not going to be going back in time. Negative time doesn't make a lot of sense to me. So I like to start my graph at time 0. And if I'm going to start this process, x is going to be a value of 0 also. So my initial component, if you look back up for a couple seconds, where I'm going to begin, I'm always going to begin at a time, at an initial location of 0, like somewhere at x equals 0 here. Now my height might not be 0. Like if I take a baseball and I throw a baseball, I'm usually releasing it from a height of 5 or 6 feet. Okay? If I kick a football, I might be kicking it from a height of 2 or 3 inches off of a tee, right? If I shoot Biff the human cannonball out of a cannon, he might be launched from a height of 4 feet. So my initial height might be somewhere like right here. So I'm going to probably end up having a 0 there, but potentially an initial height. So that initial coordinate where I am, I need to mark that. And you can see back on these equations, there is no initial x value because I want to start with x equals 0, but there often is a height value that I'm going to have before I start dealing with the velocity here. Now, just like there's an x velocity, right, x component, there's also a y component. How do you think I'd find the y component? Instead of using cosine of 55, I'd use what?
Sine.
I use sine of that angle. And that would be y over that initial velocity. And when I multiply, I get y equals VO sine of 55. Well, that's this. Okay? So what this is saying is, okay, I'm going to start at this height, but I'm going to be moving in the y direction this much for each unit of time. So what happens if I didn't have gravity is like at time 1, like I'm starting here, right? I might say at time 1, I've moved this much in the x, this much in the y. So say at time 1, I've moved this much in the x, this much in the y, and I put it up. And then I'd say at time 2, now this is if there wasn't gravity. At time 2, I would move again this much in the x and this much in the y. And I would get all these points as time was changing. But we know that's not what happens here on Earth, or really on any planet, because a planet has mass, and mass pulls towards itself, right? Even you have a gravitational element where you are actually pulling something towards yourself, except your mass is so small, it's not measurable, okay? But on a huge, large body like the Earth or the sun or the moon, it's pulling it towards itself. Now, the Earth is bigger than the moon, right? So you see somebody in the moon when they jump, it's like, it looks like they're in slow motion. Well, they're really not in slow motion, right? The gravity's just not pulling them down as quickly, right? Here on the Earth, we jump and it pulls us down more quickly. On Jupiter, our bodies would just implode. We would just collapse because we don't have the strength. It'd be like if 20 people hopped on top of Spencer. I know he's got some muscular stature or whatever, but if 20 people jumped on top of him, he's going to just crumble unless he can support the weight of 20 people, right? Dang, Paul. In college, we played pledge football, and I scored a touchdown, and my pledge brothers jumped on top of me and broke my rib. Like literally, I was on the bottom of this pile. You're always like, oh, it hurts because there's so many people, and I heard this crack. I'm like, freaking get off of me. And I blew it off for a day, but it was like creaking. I went in that broken rib. Anyway, so my guess is, on Jupiter, where the mass is so big, the gravitational pull is so much. Imagine that. It's like being pulled to the Earth so much, our body's not accustomed to that. And it would literally start crumbling under its own weight unless you were built really, really well. And I don't think any of us, I don't know what the force is, but Jupiter's so big, I think we just crumble. And of course, on the sun, even if we could cool it off a little bit, the force there, we would just crumble into dust or something. I don't know. Who knows? Nobody's been there. But are you with me on this movement? So what I do is I go, all right, I need a beginning place. That's that initial point. But since I always want to start as near the origin as possible, I'm going to start at x equals 0. And if there is a height, I'll put the height in there. So that's my starting place, 0h. And then I need to talk about the movement along x and y. So I take my velocity and my angle, my initial velocity and angle, and I separate those into an x and y component by using VO cosine 55, VO sine 55. And that's the change. That's like my slope in each direction for each unit of time that's happening. However, what else is going on? Gravity. Now, gravity doesn't pull us sideways, right? I mean, I'm not walking along and go, oh, gravity. I mean, it doesn't work that way. It just pulls down, and that is in the y direction. And gravity, if you learn in physics, has when we talk about forces, positive forces move up or to the right, negative forces move down or to the left. So if I'm talking about gravity, it's pulling down. So gravity can be measured a lot of ways because there's different units. But on Earth, at sea level, gravity or acceleration due to gravity is negative 9.8 meters per second squared. Right? Now, in my examples, I'm going to use feet. So instead of meters per second, I'm going to use feet per second squared, and that would be negative 32 feet per second squared. All right, now, the way gravity works, and you won't really know this until you learn integration and how to take a derivative, but when you when you apply some calculus to these formulas, this shows up, okay? When you apply some calculus, you end up raising the power and then dividing by that power, and you get this unit. Well, what this unit over here, this represents the gravity, and again, there's no point in explaining it any more than that because it's calculus-based, but you'll see that, I think, when you take C physics, if you take C physics. So right here, what this means is the acceleration due to gravity is that negative 32 here on Earth, and all of our examples will be here on Earth. So you take that negative 32, or if you were in the physics class, negative 9.8, I think they even let you get sloppy with negative 10. But you take that negative 32 and you plug it in there for A, and it gives you negative 1/2 of negative 32 t squared. And that ends up being negative 16 t squared. And that does the gravity component. And since gravity only pulls in this direction, that movement that I had a second ago, it was looking like this linearly, really doesn't move linearly, does it? Because the gravity is pulling it down, it ends up pulling each of these points down, and that's what creates our parabola. Are you with me? Because it's always a minus. So instead of being right here, it's down a little bit, here, down a little bit, here, down a little bit, down a little bit, down a little bit. And eventually it's just moving down until it either hits the ground or hits a wall or whatever it is that stops that projectile. Are you tracking? Okay, so the upside of this is it should feel a little similar. It does have a parabolic element to it. There's a lot of things about parabolas that we know, like how to find the max is a vertex, you know, how to find out the x-intercepts when you plug in 0 for y. There's lots of different things that we can find about this, but essentially what we're doing is we're taking this parabolic movement and separating it into an x movement and a y movement. So this right here is going to show x movement over time. Okay? The y coordinate is going to show y movement over time. Okay? And then putting them together shows the parabolic movement over time. But each of these basically are measuring just that part, that parameter of this movement, hence the parametric equations. All right? So with all of this, make sure you know what these variables represent. But we're going to be basically using these two equations. So these are the two equations at the bottom of page 71. I think it's page 71 for you guys too. But those are the two equations that we're going to be using exclusively. I'm not going to make you remember the negative 32 thing, but you need to know that VO means your initial velocity. Theta means your angle at which it was shot. T, there, and there, that's your time element. That's how long you have been going at any particular point. H is your initial height, right? And then finally, what do X and Y represent? Say it again.
Final X position and final Y position.
Could be, but actually X and Y represent any position. So it depends on your time. So at time 1, if I plug a 1 in there, it represents my X movement at 1 second or 1 hour or whatever, my Y movement. At x equals 7, it would represent my X movement at 7 seconds, Y movement at 7 seconds. So at any point in time, and people get this confused sometimes, they go, oh, Y is your initial height. It could be your initial height, but really H is your initial height. But if I plug in a 0 there and there, all that goes away, and it is your initial height. But y and x represent my movement along the horizontal and my movement along the vertical at any particular point in time. So if you know that time, you can plug it in and you can find the position that you're located in each of these, whether it's the horizontal or the vertical plane. And you put them together and you have your location in your space. Are you seeing this? Okay, I want to walk you through some of these. Our challenge is to be able to do these with algebra. And then I'm going to also show you how to use your calculator. Last year's group was like, Mr. Hurry, you showing me the calculator. It's easier for me to just do the algebra. Can I just do the algebra and not show my work and it'll look like I did the well, I'll have no way of knowing. On your test, you'll have your calculator throughout this section. It'll be a 2-section test. You'll have the polar graph part that's no calculator. Then you'll pull the graph and calculate it and do the parametric part. But when you do this, yes, if you want to use your calculator program, because your calculator can actually graph these, and you can use some of the features of your calculator to find these things, these values, which is great. But some people go, man, the algebra, I know the algebra pretty well. I'd rather just do the algebra. That'll be your call. But I will make you be accurate up to a certain decimal place, and I'll show you how to do that. So let's just talk about one of these examples. And I think a lot of people learn better from that anyway. So according to this, you got a kicker on a football team. He's trying to kick a field goal, right? So when he kicks the ball, it is currently located on the ground. So that means my initial height is 0. So I have a 0 for h. He kicks it with a velocity of 85 feet per second. So what is that? That's my initial velocity. And by the way, in physics, you do a lot with velocity. And you not only deal with initial velocity, you might have velocity at time 1, velocity at time 3. We only use initial velocity with parametric equations. So if I told you the velocity at time 7, that's not going to help you here. All right, we need initial. All right, and then it says with an initial angle of 43. So now you know your angle. Okay, it says what distance can he kick the ball if he has to get over the goalpost, which is 10 feet high? Well, currently I come in here and I put the 85 in there. I put the 43 in there. I put the 0 in there, and I've got a pretty good set of equations. I don't have anything missing on these. And I could type these in my calculator, and I'll show you how to do that later. And I could graph a really nice parametric equation representing this field goal. But we have everything. We're going to show manually how we can actually do some of this. And by the way, there'll be problems where I'll say use the graphing capabilities of your calculator. That's different for me than saying you're always welcome to use your calculator to crunch numbers and to find decimals and all that kind of stuff on this part of the test. But the graph, sometimes I'm going to ask you to do it without the graphing part, which means you can use it to find the sine of 24, but you can't use it to graph. And you have to show me the setup in the algebra. Y'all seeing the difference? And then when I get to the graphing part, all I want is an answer. That's it. Stay with me, guys. Okay, so the question was, how long will the ball have been in flight when it goes through the goalpost? Now, what do you know about the location of the goalpost? Because I don't know how long that's going to take right now. What do you know about the location of the goalpost based on this? It's 10 feet high. So if you think about the image of this, okay, I'm kicking it from the ground, right? It goes up into the air and it's coming back down. And evidently there's a goalpost right here, which has a height of 10 feet. So I want to be able to go. I have no idea on this point how far I've gone. But I do know what? The height has to be 10 feet. I don't overthink this. I know technically it's going to doink off the goalpost if it hits right at 10 feet. But just work with me. All right. So 10 feet right here. And I have no idea how long it's going to take there to get there. But what I do know is I don't know X, I do know Y, and I don't know T. But I do know Y. So if I know that Y is 10, and I take that 10 right here, and I shove it in there for Y, what's missing in this? T. And if I look at this, I see a quadratic equation. I got a T squared, and I got a T. Now, I'm used to seeing X squared and X, but it's still T squared and T, right? I can solve this. Now, how would you solve it? Some of y'all are waiting for somebody else to talk. Quadratic formula. Now, I'm not going to be able to factor this because, good night, what the heck is sine of 43? That's going to give me some horrible looking decimal. Even if it was sine of 45, I got a root 2 over 2 in there. How am I going to factor that? So I'm just going to plan on having to use the quadratic formula whenever I have to solve a quadratic. Now, if you're like, well, why did you use that equation? Why didn't you use this equation? Well, it's because I didn't know anything about x. But if I had told you, hey, how high is it? If it's 200 feet away, you're darn right I'm going to plug 200 into there, find the time it took to get there, and then reuse it to find the height. I just didn't know anything about x, but I did know something about y. And remember, the time it takes to go this far is the same time it took to go that high. So this time right here is the same time that goes with the height as well as the distance. So I can link these two equations with time because they share that same t for each point. Now look at the math on this. I've got to actually be able to do something with this. So I'm used to solving quadratics when they're set equal to 0. So I'm going to subtract that 10 to whatever this value was. In this case, it's 0. And I get a quadratic. Now, look at this quadratic. Every time you do this work, you are going to have, and by the way, this is not really in the normal order. We normally have x squared x and a constant, right? If you're plugging it straight into these equations, you're going to have a constant. That's going to be like your c. All of that is going to be your b. And then negative 16 is going to be your a. Are you with me? Now, for those who are like, oh, I don't really feel comfortable with a being negative, so I'm going to multiply through by negative. Knock yourself out. I don't care. To me, it's just not a big deal. So what I'm going to do is acknowledge that that's my c, my b, and my a, and I'm going to plug it in the quadratic formula. Now, before you start plugging it in the quadratic formula, I want you to see something. Think about what you would have to do to plug this in. I'm going to have to negate the b. That's not a big deal. I'll put a negative in front. Then I'm going to have to do plus or minus. Well, that's kind of a big deal. I can't do both at the same time, right? So I could start with plus, do that whole equation, hit enter. Literally, how are you going to type that in squared? Now, the 85 squared part, that's not a problem. But how do I square sine of 43? Well, I end up having to put all these parentheses in there, don't I? So I have all these extra parentheses because I can't sneak a 2 right there to square the sine. So I end up having all this extra parentheses. You know what I do? I just go ahead and calculate b ahead of time. So what I'm going to do is type in 85 sine of 43 in my calculator and hit enter. It's going to spit that out. Do you know how to store values? So it's really easy. Check it out. On your calculator, you have a stow button right over vars. You see it? Store. So what all you have to do for something like this is you're going to type in, let's just say I type in, and I need to make sure I'm in degrees, I type in 85, what was it? Talk to me.
Sine of 43.
Sine of 43? So 85 sine of 43 degrees, and I hit enter. And there's my 57.970. My calculator currently is rounding to 3 decimals. I kind of like 5, but I was doing some application on this with calculus and whatever. So whatever it is, notice that when I go and grab that number and I hit enter, look what it brings down. All the number, okay? So I have that number right here, but look at this. As soon as I hit enter, I'll show you the whole process again. I hit enter and I get that value. All I have to do is store it as B. So if I go to store, which is control vars, it puts a little answer arrow, and then you pick the variable. So don't pick X, by the way, or Y or T, or it messes up all your parametric equations. Don't do that, okay? And you'll be like, why is my calculator messing up with all my graphs? It will think every time you type an X in, it's equal to whatever that decimal is. So don't do that. Pick numbers like A, B, M, P, numbers you would normally never use. So I'm going to store it as B. I hit the little B variable, enter, and from here on out, I can use B in my equations. Are you with me? So now, when I come back, I can go fraction. Here we go. I can use the fraction button, and I can go negative B plus the square root of B squared. See how much easier that is? And it's in there. And then I can go minus 4 times the A value, which is negative 16, times the C value, which is -10. It's all in there over what? Twice the A value, which you can write 2 times -16, but I think I can handle that, -32. And I can hit enter, and it gives me the time it took to get to that height. Now, that doesn't make any sense. Who kicks a field goal, and it's at a height of 10 feet in 0.1 seconds? Can you make sense of that? I can. It hit 10 on the way up. So you got to make sense of that. If I'm kicking a long field goal, it's probably going up and coming back down. So that going on the way up, and technically they both would make sense. You can kick a field goal where it's still rising and it goes over. I mean, extra points almost all do that, right? When you kick an extra point, it's still going up. I mean, it's slowing down a little bit, but it's still on its upward part. So right here, that's the first one. Then I go back, grab that equation, and go and change it to the negative option, not the minus option, but the negative option. Hit enter, and that's the other time. That's the time coming back down. And if one of your times happens to be negative, well, that kind of makes sense too. Think about it. What if I kick this from a height of 20 feet, right? Well, the calculator is going to give me the times when this was at a height of 10, which is there, whatever that time is, and also here. That's also a height of 10, which doesn't make any sense, but my calculator doesn't know I'm talking about kicking footballs, does it? It just thinks it's a parabola. So if you ever get a negative time, then you can just kind of discard that because we aren't going back in time on these, right? You with me? So back to my right here. Hopefully that will make sense with your calculator, but I would do that. Go ahead and find that B value. By the way, on your test or on your work, make sure you write B equals. That'll be good practice for calculus as well. On calculus, if you're going to use a variable, you have to define it. You have to say like A equals blah, and then from there out, you can use A in your work. So say B equals whatever, show it, and then all you got to do is show your setup with B's. So those are my two values. This is the one that really makes sense, although in this case, you can argue, unless the problem specifically said on the way down, it says as it goes through the goalpost. So yeah, it didn't specify that. It didn't like if it was shooting a basketball, what has to happen? It has to be coming down because it has to go through the hoop, right? I can't shoot it through the bottom of the hoop and it actually count. That doesn't work, right? So you would have to be the final one. And another thing, by the way, if it is the final one, it has to be positive, right? And it will be the biggest time, won't it? If I'm dividing by a -32 each time, assuming I don't change my A value. If I'm dividing by a -32, what sign on the top do you think is going to give me the biggest value? The minus one, because I want a negative minus a negative to get a bigger negative. So that when I divide it by a negative, I get a bigger positive. So a lot of times, if I know I just want the ending one, when I go to my calculator, I only do the negative B minus. But you're welcome to do both. Okay, that's what I did on this key. So right there, you can see it. I did the negative B plus version, the minus version. I got my two values. Now I know time. But what was the question? How far? So how long will the ball have been in flight? I now have that, right? I know the times it took to get to the goalpost, right? Or at least to a height of 10 feet. So I could have been really close, height of 10 feet, reached the goalpost going up, or I could have been far away, height of 10 feet, got the goalpost after 3.4 seconds or whatever. And then the set said, what distance can he kick the ball? Now, how would I take that time and find distance? Plug it back into your X equation. Because that same time will tell me how long it took to get to a height of 10 feet, but I can also use it to find the distance that I traveled. So what did I do? I took both those times and I plug them back in here. I used this one because it kind of seemed like it would be a maximum distance right here. Oh, actually it said the furthest distance. Okay, so I put the, so it did specify that. So I'm going to take the 3.441, whatever, the whole exact value, don't round ever. Always use the exact values so that I never get off. And I plug that back into the X equation for T, and it spits out the distance in the time travel. Are you seeing that? Still got 2 or 3 minutes. Okay. On a. All right. I'm not going to be able to get very far on this, if anywhere. So here's what we're going to do. We're just going to make sure you go home, study this sheet up, feel pretty comfortable with it. I don't know that we're going to be able to finish up this classwork, so we'll finish up the classwork tomorrow, and then we can do the homework tomorrow night, and we'll be okay because it's really just a homework sheet. And then on Friday and over the weekend, we'll talk. You'll have 2 reviews to kind of keep you fresh. The homework for projectile and the review number 3 for polar. All right.